Okay, today we're going to look at the mole concept, which is a brand new concept and one that takes a little bit of time to understand. The mole is odd because when you think of the mole, you think of an animal, right? But in this case, we're actually looking at what we would call instead of a baker's dozen, a chemist's dozen. So for example, in typical everyday life, we would use things like a dozen. You've probably never heard of a gross, maybe you have, but a dozen to describe something that is important in a measurement. For example, if I want to get a dozen donuts from Dunkin' Donuts. So that's one thing we use constantly, a common term that describes sort of that a certain count of a number. So we do that a lot. Now, like I said, a chemist's dozen is going to be the mole. And it's odd because if you think about it, when you're looking at this here, up at a dozen here, you're saying, well, a dozen is a number that describes just 12 objects. And we're talking about tangible things you can see. But when we're talking about particles are so tiny that we actually have to use a humongous number right here. So when you look at 6.02214 times 10 to the 23rd, the only way we can really understand it, the idea of a mole, or understand particles or molecules or atoms, is by saying, okay, we got to get a lot of them, a big handful of them, to understand it. So if we want to understand something really tiny, we're going to use a whole bunch of them to understand it. And this, again, this number, this huge number, 6.02 times 10 to the 23rd, is called Avogadro's number. And where did it come from? This guy right here. He's a pretty famous chemist, physicist, and he came up with this number. And the way he came up with the number we'll talk about here shortly. But the mole can really specify anything as far as Avogadro's number is concerned. And so, for example, a mole of marbles would be 6.02214 times 10 to the 23rd marbles. The same thing with sand grains, which would actually make sense because sand grains, again, are very tiny. 1 mole of anything equals that number, Avogadro's number, units of that thing. And the second thing, and this is really the thing we should really wrap our heads around, because it's the thing that makes the most sense, because we probably don't care about marbles or grains of sand when it comes to chemistry. But the number that Avogadro used for this was basically the value of carbon-12, so the most stable isotope of carbon. 12 grams of carbon equaled exactly 6.02 times 10 to the 23rd atoms of carbon. So this is where it all started. And in everything in chemistry, we have to come up with some sort of like standard. So the standard in this case would be, we're going to use carbon. And carbon makes sense because we're made up of a lot of carbon. The Earth is made up of a lot of carbon. Carbon's a good one to use because it comes in 3 isotopes, with carbon-12 being the most stable and the most well represented in the universe. So what are we going to do with this? That's the next question. What's the point? And the nice thing is you're going to see some pretty easy applications right away, so that you won't question why in the world we're doing this. So we spent a lot of time converting between number of moles and number of atoms, just like we would say, I just bought 3 dozen donuts. So how many did I get? You could do the same thing with that. So for example, for atoms, we would use this conversion factor. So remember when we did it before, we could say, well, 1 dozen equals 12 items. In this case, we're just going to take 1 mole and we're going to put Avogadro's number on the bottom there. And I probably am going to run out of room, but that's okay. So this is a conversion factor that we would use. And of course, I need to put atoms right beside 23, but that works. And so again, there it is right there. That's a lot better. We can either use it this way or this way, depending on how we need it to work. And we talked about that a lot before. So let's take a look at some examples. Before we take a look at an example, though, to count atoms by weighing them, we need a conversion factor, 1 mole of atoms. So the mass of 1 mole of atoms of any element is the molar mass from the periodic table. So for example, if you look at oxygen, it's 16, 15.994. Or if, like we said with carbon, 12.011. A mole of atoms, so 6.02 times 10 to the 23rd atoms of a certain element, any element you want, is going to equal the molar mass, which comes from the periodic table. And again, the whole point of this is to come up with a standard. And we use these things called AMUs, atomic mass units. And again, standards are what we're going to, it's sort of like if you were going to travel, and we're not doing a lot of traveling right now, maybe you're doing a little bit of traveling over fall break. But the point of this is, if I go to a different country where the units of currency are different, I need to have a conversion rate. The same thing is true. I need to have a standard somehow. Somehow there needs to be a standard that this amount of Canadian dollars is worth this amount of euros, which is worth this amount of US currency. When I look at the different elements on the periodic table, each one has to have a standard. So carbon's worth 12.001, oxygen's worth 15.994. Those are kind of like our countries and how we go in between a conversion rate. So if we look at a question, we're going to convert the number of moles to the number of atoms. This is actually one of the easier ones. So say you were given, right here, 2.45 moles of copper. And again, moles are like the standard. We can work within things. Two elements work together if we have the moles of each one. And that'll make sense because it deals with ratios. We'll talk about that soon. So how will we do that? Well, we want to convert the number of moles. And we use Avogadro's number. So the conceptual plan, our flow chart is right here. And that flow chart would say I want to go from moles of copper to copper atoms. So I'm using that conversion rate, but exactly how am I using that conversion rate? Well, let's go to the next slide, and we would see that I would go with what I was given, 2.45 moles of copper. And since moles of copper are on top, we put moles of copper, we flip it, and then we take it right there. We multiply these things. Notice I started with 3 sig figs. This is a conversion, so this has infinite sig figs, so we don't care. 3 sig figs there. Use your calculator, and you find 1.48 times 10 to the 24 copper atoms, which you might be saying, who cares? But it actually ends up being important later, I promise. So that kind of makes sense because if you think about it, it's 2.5-ish times larger than what we started with. Let's look at the next one here. Calculate the amount of carbon in moles contained in your pencil. So we go take your pencil and we strip out the graphite, we put it on our balance, and we find that it's a very tiny mass right here. And I want to say, okay, how many moles do I have there? And so I start with this mass right here. And since I have this mass, what I can do is convert that to moles. So in this case, I'm going to go to the periodic table and I'm going to find the fact that I know that 1 mole is not only 6.02 times 10 to the 23rd atoms, but it's also 12.01 grams or AMUs. And that's why the periodic table is so nice, because a mole can do 2 things for me. It can tell me number of atoms using Avogadro's number, or it can use the periodic table to tell me the grams that make the standard mole so that we can kind of go from country to country in the currency conversion, if you want to think about it that way. So I'll use this conceptual plan. I'll put grams on top. If grams are on top to start with, grams are on bottom here. And then I can get a tiny, tiny number, which again makes sense because it's a tiny, tiny mass. And I have a very small amount of moles of carbon here. So that doesn't make sense. Maybe pause it, rewind it, and check it out again. So let's look at the next one, converting mass and moles. So again, here we got kind of a schematic here that shows that basically when it comes down to it, the lighter the atom, meaning something like helium, for example, is pretty light, 4.03 grams, and that 0.03, excuse me, and that comes from the periodic table. It's a tiny amount of mass, but it's still, again, all of these masses come from the periodic table, your new best friend, and all of these are the same because we're talking apples to apples moles. And that gives us, in the future, a great way to work in between. Converting between mass and moles, then we're just going to say, okay, well, if we know the molar mass of any element is a conversion factor between grams and moles, For carbon, then, we can just, again, use these conversion factors. Again, this is like saying 1,000 milliliters equal a liter. It's the same thing, and that's why we spent so much time going over that, so that now we have these nice conversion factors. There's one way, flip it the other way. Now we can use it to get things done. For example, if we're given grams again, can we take it and convert it? Well, we just did that, and that's why we used that conversion rate. So just to kind of review this again, that's why we took the moles and we put it on bottom. Again, kind of just a little replay there in case you missed it the first time, and that's no problem at all. The mole concept, converting mass to moles and atoms, again, this sort of comes to a two-step problem, which we can do no problem because we're not only going to use what we got from the periodic table, but we're going to use the fact that we know that 1 mole of copper equals the number we use, Avogadro's number, of atoms. So if we said, how many atoms do we have? We just do a two-step problem. So let's do it. Here's my find over here, copper atoms. Here's my given, 3.14. And I'm simply going to use these two conversion factors that I just figured out. Since I have 2 arrows to solve, if you go back to the review there, you can see that what we have here is 2 conversion factors. Grams on top, grams on bottom, moles on top, moles on bottom. What am I left with? Atoms right there. So we can use pretty much these conversion factors to do what we need to do to get this done. So whether it be a 1-step problem, whether it be a 2-step problem, that's just a real quick flyby of how the mole actually helps us. You might be thinking right now, I still don't know what a mole is and why it's used, but hopefully you can at least take the idea that the periodic table atomic mass equals 1 mole of anything, and that the number of atoms, molecules, or ions, in this case atoms, equals that many, 6.0 times 10 to the 23rd, and that is going to be equal to 1 mole, okay? So hopefully that helped you out. Hopefully that makes sense. I want you to do some practice problems, and again, not everything may make sense now, but this is sort of a rough flyby, getting to know you, the mole, all right? Check it out, see what you got, and we'll talk about it more in the next few days. Lots and lots of practice, all right? We'll see you.